Good afternoon everyone, I am Mr. Ish. Thank you for joining me on this video. We are looking here at rate of change of integrals, and they are very important indeed. So if you think about it, these derivatives, when you integrate them, you see these applications come about in the variety of natural sciences out there. You're essentially, with regards to rate of change integrals, you're looking at some sort of a derivative. We'll call that a function at time t, and you're basically integrating it. And you're looking at applications which arise as a result of this expression or this procedure. And in all of these examples, or let's say the three examples that I'll present to you, in all of these instances, you'll see that time plays a very important role. Time is indeed a factor in all of this. And of course, what you're looking about is the initial amount, or whatever it is that you're looking at, initial amount at time, initial time, and then you're looking at some sort of final amount. And we have something here with regards to amount at time t. Let's just use here as an abbreviation. We can use, let's say, FO or FT, the amount that you have at initial time and the amount you have at time t. And in all of these instances, the rates of change integrals are usually dependent on this, and they're dependent on this, or they're dependent on this, the final amount or the initial amount. So with all of these applications that I'll show you, three of them, I want to breeze through them and try to make this video short but to the point and interesting. If you think about money, if you have a certain principal at time 0 or initial principal, and then you let it sit in a bank at a certain rate, an interest rate over a period of time, it grows to a certain amount at time t. Derivative or derive a derivative and then integrate it, you could come up with a very interesting formula, and I'll show you. Here you're looking at some sort of a change in principal over a period of a time dependent on some rate and the amount that you're starting with. So how can you look at this rate of change and integrate it? You have to first set up creating a derivative, and you can do so this way. If you look at a certain change in principal over a change in time, see dp or dt, change in principal over change in time, and we're looking at something positive here because over time money grows. Generally money grows, hence the positive, is equal to this rate. We'll call it k, or we can even use, in this instance, the rate and interest rate, we can give it the symbol r, and then we have this p. All you have to do here from this derivative that we've created is switch the dt and the p, and you'll have something which ends up as this dp, or this p, this is my principal, is equal to r dt. Now we're beginning to create something which looks like an integral, and we have to do nothing more than this. We have something here at an initial time, principal at initial time, and principal at time t. Here we have something at initial time, we'll call that 0, and at time t. In all of these instances, you're looking at integrals of polynomials. Here you have something which looks like p to the power of minus 1 because it's 1 over p, and you know how to integrate this. Here you have a hidden antiderivative like t to the power of 0, and you know how to integrate this, n plus 1 or n plus 1. Here this brings in the natural log. When we do the definite integration here, these integral signs go away, and we end up with this natural log p, and you know you're looking at upper interval, lower interval is equal to rt. Upper interval, lower interval, t and a 0 are meaningless in this sense. You have to do the definite integration here with regards to upper and lower limit, and you have natural log that minus natural log the initial amount is equal to rt. Everything here is positive because money grows over a period of time. And then you can combine everything using a common log, and the properties of logs is equal to rt. Take the natural log on the other side. The principal at time t, which is the latter amount, is when divided by PO, the initial amount is equal to ERT, and then the final amount over a period of time is equal to initial amount times this natural exponential base to the power of RT, and here you end up seeing this wonderful formula for continuous compound interest, and you know that, and that's exactly an excellent example for a rate of change integral, that the value of your money over a period of time is dependent on the initial amount times the natural exponential base to the power of your rate and your period of time, and this is a continuous compound interest where money is compounded continuously. For this rate of change integrals second example, we look at the concept of radioactive decay. Many of you might be familiar with that. In a decay process, you're starting out with a certain number of nuclei, which over a period of time you can have initial and you have a final amount over a period of time, the number of nuclei which you started out with decrease. So as reaction proceeds, this value decreases, the initial isotope decreases, and these daughter isotopes which form, which could be very much different than what you started with, increase with time. In these instances, you're looking at a negative rate of change, because as the reaction proceeds, the thing you're looking at, this NO, the initial nuclei or the atoms that you're studying, they decrease with the period of time. So you have to establish a derivative with regards to this negative. You're looking at essentially a change in the number of nuclei over a change in time minus is equal to some sort of k rate constant multiplied by, of course, the number of nuclei that this reaction is dependent on, the initial nuclei. You can flip this dt and n. You can have minus dn over n is equal to k dt. You could take the minus and bring it across. Now you have a derivative very well established which can be easily integrated. This case stands outside the integral sign because it serves as a coefficient. You're only bringing integrals with regards to the variables, a hidden variable here and your apparent variable here. Here you'll have a number of nuclei initially and the number of nuclei or daughter isotopes or daughter nuclei which result over a period of time. Here you'll have initial time, here you have final time. This right here is easy to integrate. You know, it brings in the natural log and natural log n. You have nt, no, upper and lower limits is equal to minus kt. You can expand this out. Natural log nt minus natural log no is equal to minus kt. You can bring everything here if you want, or you can just take this natural log on the other side, keep this a linear equation, but I want to make this into an exponential style equation. So I'm going to bring everything under a common log. Natural log nt over no is equal to minus kt. Again, the minus here signifies that this initial parent isotope that you're looking at, or parent nuclei, will decrease over a period of time, hence the minus sign. Nt over no is equal to e to the minus kt. You could use or here instead of k. I use the letter k. The number of nuclei or daughter isotopes at time t is equal to the number of nuclei or isotopes, the parent isotopes, times e to the minus kt, which gives you the equation of nuclear decay. If you want to take this one step further, you can actually study the concept of half-life, which you know represents the time it takes for a reaction such that the initial value of these parent nuclei are decreased by half. But the time required for this initial amount to become half of its original amount, that's your half-life. You can use this equation right here to determine an equation for half-life. How do you do that? Well, at half-life, you know that the final nuclei is always equal to the initial nuclei over 2, right? The final resultant nuclei or daughter isotope should equal to your initial isotope, half of that. So where you have nt, you can substitute for no over 2. No over 2 is equal to no e to the minus kt. Or if you want, you can bring all of that into this equation right over here. Or we can just proceed from right here. You can take this on the other side. You'll have no over 2no is equal to e to the minus kt. These cancel out. 1 over 2 is equal to e to the minus kt. Get rid of this exponent. You have natural log 0.5 is equal to minus kt natural log e. Natural log e is meaningless because it's equal to 1. Here t means half-life, t half. Or if you want to be a little sophisticated here, you can do natural log 1 over 2 is equal to minus kt. Remember, we're coming up with the equation for half-life. You see 0.5 is the same thing as 1 over 2. You can use a property of logs and separate this. Natural log 1 minus natural log 2. 1 divided by 2, the quotient of a natural log, common log, is equal to the difference of their logs. See, this minus comes out from right here, is equal to minus kt. We know natural log 1 is equal to a 0, so we have minus natural log 2 is equal to minus kt, and now I'll bring this t half, half-life. We're solving for t half. T half, half-life, is equal to minus natural log 2 over minus k. T half-life is equal to natural log 2 over k, or 0.693 divided by k, and this right here is your formula for half-life of a reaction which is talking about a radioactive decay reaction. A radioactive procedure has a half-life which can be measured using this. The half-life is natural log 2 divided by the rate constant. The rate constant can easily be algebraically calculated if from this equation. If you know the final amount, the initial amount, and you know the time, you can solve for k and you can have this value. Now, as our last example for this rate of change integrals, we're looking here at an example involving chemical kinetics, reaction rates, a concept which is frequently studied in chemistry. If you have a certain, let's look at two reactants coming together to give you a certain product, and there's a certain rate of this reaction. How can we go about developing a rate law for this type of a reaction, a rate law? And this ends up involving two reactants to give a single product, and as the reaction proceeds, these will decrease and this will increase, so you have some sort of rate which will be such it'll have a minus, because the concentration of these two will decrease with time and the concentration of this will increase with time, at least initially. And generally here the rate of these types of reactions is dependent on time, and of course the final amounts of these. With reaction rates, generally it's dependent on the final concentrations of these rather than their initial. But anyhow, the reaction derivative can be established this way. Here that you're looking at the change in the concentration of this material, which is called A, over a period of time is equal to some sort of rate constant. We'll call that K times A times A. Why am I doing times A times A? Because there are two of these. See, there are two of these, and this right here is equal to KA square. And then dA over dt, we'll bring in these minus signs over here. We can flip this and we can flip this. We'll have minus dA over A square is equal to K dt. We can bring the minus across. dA, change in concentration of A over A square, or the derivative of A with respect to A square, is equal to minus K dt. Bring the integral signs right over here. Here we'll have our lower limit of A, O, which is our initial concentration. Here we'll have the concentration at time t. Here we have initial time and final time. You have something over here which you're looking in terms of a polynomial like this, which is equal to a to the minus 2. Then you do plus 1 and n plus 1, and that's easy. So when you do the definite integration or the antiderivative of this 1 over a square, you'll get minus 1 over a. From an upper limit at and lower limit ao is equal to minus kt. Think about it. This right here, it will give you a to the minus 1 or minus 1, which is minus 1 over a, which you see very well right over here. And you can open this up, do your definite integration procedure of this antiderivative. You'll have minus 1 over at minus 1 over ao. Don't make a mistake here in the arithmetic part, and minus kt. Here you have minus 1 over your concentration at time t plus 1 over concentration at time o is equal to minus kt. Take this on the other side. Minus 1 over at is equal to minus 1 over ao minus kt. You can hit everything here with a minus and change all of these minus to positives, and let's do that. And you end up having this equation right here. 1 over at is equal to 1 over ao plus kt. Your final concentration, its reciprocal, is equal to your initial concentration, its reciprocal, plus the rate constant times time. And here the reaction rate is dependent on the time, of course, and the concentration of your reactants over a period of time. And this right here is what's called the second order rate law. And this is how you can derive it, and you derive it using a rate of change integral. You're doing a derivative, or you're deriving a derivative, and then you're doing its integral over a period of time. And you can do this. You can do this not just for this, you can do this for zero order, first order. You can do this for a variety of different types of rate expressions or rate reactions you have. Then you can come up with their rate laws. And that's all I wanted to present in this video, how these types of concepts are pervasive in the variety of natural sciences out there. And I hope you enjoyed this video. Thank you for watching. Have a nice day.